All right, let's dive right in. Today, we are talking about something truly revolutionary. We're looking at how artificial intelligence is completely changing the game in one of the most important fields out there, the hunt for new, life-saving medicines. But, before we can appreciate the solution, we really have to understand the problem. And trust me, it is a massive one. Finding a single new drug is one of the most complex, expensive, and frankly, time-consuming challenges that scientists face. So the big question is, why is it so incredibly hard? So let's start with just the mind-boggling scale of this challenge. We're talking about trying to find one single, effective molecule in what is, for all intents and purposes, an infinite universe of chemical possibilities. This number right here, this says it all. For every 10,000 compounds that look promising in a lab, only one, just one, will ever make it all the way through the process to become an approved medicine you can get at a pharmacy. I mean, those odds are absolutely staggering, and they just scream for a smarter, more efficient system. So, for decades, how have scientists dealt with this needle in a haystack problem? Well, let's break down the classic methodical approach, the gold standard that's been used for a very long time. The traditional way of doing things is kind of like being a detective with a ridiculously long list of suspects. First, you've got virtual screening, where scientists filter a huge library of potential drug molecules. Then, for the ones that make the cut, they use molecular docking. That's basically a computer simulation to see how well each molecule might physically fit into a specific target protein in your body. Think of it like trying to find the one key that fits a very specific lock. And finally, after all that, scientists have to manually look at the best fits to decide which ones are actually worth pursuing. And this quote just hits the nail on the head. The classic method, it's valuable, no doubt about it. It works. But it's also a massive bottleneck. When your list of potential molecules explodes into the millions or even billions, this step-by-step process just can't keep up. It gets totally bogged down. It's too slow, and it costs way too much time and computing power. Okay, but this is where things get really, really cool. Let's introduce the hero of our story, an AI model that isn't here to replace the old process, but to supercharge it, to make it way smarter, way faster, and a whole lot more effective. And this little comparison really lays it all out. The traditional hunt is slow, methodical, and limited by resources. The AI-powered pipeline, on the other hand, is lightning fast and can easily scale to look at millions of molecules. But here's the real game changer. Look at the goal. It's a total shift in strategy. Instead of spending all that time trying to find a single perfect fit, the AI's job is to quickly predict the most promising candidates, basically telling the scientists, hey, look over here. This is where you should focus your energy. So how in the world do you actually teach a machine to be a world-class drug hunter? Let's get into the nuts and bolts of how an AI like this is actually built and trained from the ground up. The whole thing really breaks down into 3 clear phases. First, you got to get the data ready. Second, you do the actual training of the model. And third, you have to test it to evaluate how well it actually learned its lessons. It's a clean, logical structure that makes the whole process work. Right, so the very first hurdle is figuring out how to teach an AI to understand the language of chemistry. The way we do that is by translating these complex 3D molecules into something called smile strings. You can just think of it as turning a complicated chemical structure into a simple line of text, a sentence that the AI can actually read. Now, the brain of this whole operation is a powerful AI architecture you've probably heard of, a transformer. This is the same kind of tech that powers the most advanced language models out there. It's absolutely brilliant at finding patterns and understanding the relationships and sequences, which makes it perfect for reading those chemical sentences we were just talking about. And how do we know it's actually working? Well, we can literally watch it learn. This chart shows what's called training loss, which is just a fancy term for its error rate. With each pass through the data, each epoch, that loss goes down. You can see it right there, dropping from 2.09 to 2.05 and then down to 2.04. It's clear, visual proof that the AI is getting smarter and more accurate with every single cycle. So, the model has graduated from training school, but now it's time for the final exam. We have to see how well it performs on brand new data it has never ever seen before. This is the real moment of truth. To grade the AI, we use a few standard metrics, and you definitely don't need to be a data scientist to get this. Just think of MSE, RMSE, and MAE as different ways to measure how far off the AI's predictions are from the real, true values. And for all of them, the rule is simple. The lower the number, the better the score.
And here are the final scores. This is the model's official report card. These numbers give us a hard, quantitative measure of its accuracy on data it's never seen. It's the proof that it can do the job.
Okay, so numbers on a chart are one thing, but what does this actually look like in practice? Let's take a look. We're looking at something called affinity here, basically how strongly a drug binds to its target. Higher is better. So in one case, the true affinity was about 6.96, and the model predicted an almost dead-on 6.99. In another case, the true value was 5.77, and the model predicted a 7.24. This kind of check shows us how the model is performing on a case-by-case basis. All right, so we've waded through the technical stuff, but let's zoom out. What is the real-world impact here? What does all this actually mean for the future of our health? And this, right here, is the ultimate takeaway. This isn't just about building cool AI models for the sake of it. By being able to predict the most promising drug candidates in a fraction of the time, this technology can dramatically speed up that first critical and often slowest step in developing new medicines. And that means getting life-saving treatments to the people who need them faster than ever before. And that leaves us with one last, really fascinating thought to chew on. Today's AI can learn to predict which molecules are the best. But what about tomorrow? If an AI can learn to recognize a great molecule, what's to stop the next generation of AI from learning how to create entirely new ones from scratch? Now that is the next